There is an ocean on another world that has never once seen sunlight, not for a season, not for an age. For approximately 4 billion years, it has been sealed beneath a shell of ice, cut off from the universe above it, sitting in total darkness while everything we know as life evolved, flourished, and changed on Earth. That ocean, beneath the frozen surface of Europa, one of Jupiter's moons, holds more liquid water than every ocean, river, lake, and ice sheet on our planet combined. It has been there longer than complex life has existed anywhere we know of. And until recently, we had no way to reach it, no way to see into it, and no real way to know what 4 billion years of darkness and pressure and isolation does to water. Then, in 2013, something changed. The Hubble Space Telescope detected water vapor venting from Europa's surface into space. Material from the ocean below had forced its way up through the ice. The ocean was not as sealed as we thought. Something was pushing out. That discovery quietly shifted the conversation among planetary scientists, and in October 2024, NASA launched Europa Clipper, one of the most ambitious and expensive planetary missions ever attempted, specifically to get closer to whatever is happening down there. The question driving that mission is one that most scientists choose their words around very carefully. Not whether Europa's ocean could theoretically support life, but what 4 billion years of isolation in a liquid water ocean with heat, with chemistry, with time might actually have produced, and what it would mean if the answer is not nothing. Today, we go through what we know about Europa, what the evidence is pointing toward, and why this particular moon has become one of the most quietly unsettling places in the entire solar system. Quick favor before we continue. If you find yourself coming back to videos like these, hit subscribe so you don't miss the next one. It makes a bigger difference than you might think. To understand why Europa changes everything, we need to begin with the moment it was first seen. On winter nights in northern Italy, Jupiter appears steady and bright, hanging above the horizon with a stillness that ancient astronomers trusted. In January of 1610, Galileo Galilei turned a small handmade telescope toward that light, expecting little more than a clearer view of a familiar planet. Instead, he noticed 3 tiny points beside it, arranged in a delicate line against the darkness. They seemed insignificant at first. Small stars, perhaps, easy to overlook, but the next evening, the arrangement had changed. The points had shifted position relative to Jupiter. Galileo checked again the following night, then the night after that. The motion continued. Over the course of a week, the pattern became impossible to deny. These objects were not distant stars fixed in place. They were moving around Jupiter itself. It was a quiet observation with enormous consequences. For centuries, the dominant belief in Europe held that everything in the heavens revolved around Earth. Galileo had found direct evidence against it, visible through glass lenses no wider than a few centimeters. The Church viewed such ideas as dangerous, and the conflict that followed would define much of Galileo's later life. But among those moving lights was something else entirely, something no one could yet understand. One of them was Europa. Europa is slightly smaller than our own moon, measuring approximately 3,121 kilometers across. It circles Jupiter once every 3.5 days at a distance of roughly 671,000 kilometers. For nearly 385 years after Galileo first recorded it, Europa remained little more than a distant point of light, with a name attached to it. No telescope on Earth could reveal what waited beneath its surface. When spacecraft finally approached the Jovian system in the 20th century, Europa began to look strange. Its surface temperature averages minus 160 degrees Celsius, cold enough that water ice behaves almost like stone. Yet despite this frozen environment, Europa has the smoothest known surface of any solid object in the solar system. Craters are astonishingly rare. On worlds without geological activity, impacts accumulate for billions of years and remain visible almost forever. Europa looks different. Scarred regions appear erased, softened, or replaced. Something is renewing the surface from below. Long reddish fractures stretch across the moon in every direction. Scientists call them linea, meaning lines. Some extend for thousands of kilometers, crossing each other like cracks spreading through frozen glass. The material inside them appears to have risen upward from beneath the ice, then frozen again at the surface. Even more unsettling is the age of that surface itself. Estimates place it between 40 and 90 million years old, meaning most of Europa's visible crust formed long after dinosaurs disappeared on Earth. But Europa also lives inside one of the harshest environments in the solar system. Jupiter's immense magnetic field traps high-energy particles that bombard the moon constantly. An unprotected person standing there would receive a lethal radiation dose within hours. Cleaned, and beneath all of it, Jupiter's gravity never stops pulling. With every orbit, Europa is squeezed and flexed by tidal forces, slowly deforming the entire moon from the inside out, quietly, relentlessly. Far beyond the warmth of Earth, sunlight weakens into something thin and distant. At Jupiter's orbit, the Sun provides only a fraction of the energy our planet receives. Europa drifts through that dim region, nearly 778 million kilometers away, where surface temperatures remain cold enough to freeze rock-hard minerals solid. By ordinary expectations, an ocean there should not exist at all, but Europa does not follow ordinary expectations. The source of its heat is not above the moon, it is beside it. Jupiter dominates the entire Jovian system with immense gravitational force, pulling constantly on everything around it. Europa does not travel through space alone either. Two neighboring moons, Io and Ganymede, move in a repeating gravitational rhythm with it, a pattern astronomers call orbital resonance, meaning their orbital periods remain permanently linked through gravity. For every orbit Ganymede completes, Europa circles Jupiter exactly twice. During that same interval, Io completes 4 full orbits. The timing never drifts far from this ratio. Over billions of years, the moons continually tug on one another, maintaining a delicate but relentless balance. That balance traps Europa's orbit into a slight oval shape instead of a perfect circle. As Europa moves closer to Jupiter, gravity tightens. As it moves farther away, the pull relaxes slightly. The difference may seem small from a distance, but across an entire moon, the effect becomes enormous. Europa flexes continuously. Its rocky core stretches, compresses, and shifts during every 3.5-day orbit. Very slowly, constantly. This process is called tidal heating. Mechanical stress inside the moon generates friction, and friction produces heat. You can feel a tiny version of the same effect when rubbing your hands together on a cold night. Inside Europa, the process operates on a planetary scale. The evidence sits nearby in plain sight. Io, the innermost large moon, experiences tidal heating at far greater intensity. Its surface erupts with hundreds of active volcanoes. Vast lava lakes glow across the landscape. Sulfur plumes rise hundreds of kilometers into space before falling back onto the surface like colored snow. Some regions reshape themselves within months. Io became overheated. Europa occupies a narrower gravitational position, one balanced carefully between freezing and destruction. Tidal forces there appear strong enough to maintain liquid water beneath the crust, yet weak enough that the outer shell remains frozen, not solid throughout, not molten throughout, suspended between extremes, and this balance has endured for approximately 4 billion years. The energy involved is staggering. Current estimates suggest Europa generates roughly 1 trillion watts of internal heat continuously, comparable to the total electrical generating capacity of the United States operating without combustion, reactors, or fuel reserves. Gravity alone powers the system. No flame exists there. No sunlight reaches the buried ocean. Yet Jupiter's pull never stops. Every orbit stores energy into Europa's interior and releases it again through strain, pressure, and motion deep beneath the ice. The ocean survives because the moon is being kneaded from the inside, endlessly, by the largest planet in the solar system. A magnetic field is invisible. You cannot photograph it directly, and you cannot hear it moving through space. But with the right instruments, you can watch matter respond to it, almost like seeing wind through the motion of trees. In the 1990s, that became the key to understanding Europa. NASA's Galileo spacecraft arrived at Jupiter in December of 1995 after a 6-year journey through the inner solar system, named after the astronomer who first noticed Europa beside Jupiter centuries earlier. The spacecraft entered orbit around the gas giant and began studying its moons in extraordinary detail. Among its instruments was a magnetometer designed to measure magnetic fields with remarkable precision. Jupiter possesses one of the strongest planetary magnetic fields in the solar system. The field rotates with the planet itself, sweeping enormous regions of surrounding space every 10 hours as Jupiter turns. Europa sits directly inside this rotating magnetic environment, continuously immersed in invisible electromagnetic motion. If Europa were frozen solid all the way through, little would happen. Jupiter's magnetic field would pass through the moon with minimal disturbance, producing only weak and predictable variations. But when Galileo flew past Europa repeatedly, the data showed something unexpected. A second magnetic signal appeared to be forming inside the moon itself, and it moved. The secondary field shifted direction every 5.5 hours, precisely matching the changing orientation of Jupiter's larger rotating field. The pattern behaved exactly like electromagnetic induction, a process where a changing magnetic field generates electrical currents inside conductive material. Those currents then create their own magnetic field in response. It is the same principle used inside electrical generators on Earth. For Europa to produce such a signal, something beneath the crust had to conduct electricity efficiently over planetary scales. Ice alone could not explain it. Rock could not explain it. The measurements narrowed the possibilities dramatically. Salt water could. A global ocean containing dissolved salts would conduct electricity extremely well. As Jupiter's magnetic field swept across Europa, currents would form naturally inside that hidden ocean, generating the precise secondary field Galileo observed during its flybys. The signal matched theoretical predictions with striking accuracy. The findings were published in 1998. They transformed Europa from an interesting moon into one of the most compelling locations in planetary science. But the magnetometer evidence did not stand alone. Other observations began converging on the same conclusion from completely different directions. Surface regions called chaos terrain appeared shattered and displaced, as though sections of crust had broken apart and shifted over softer material below. Rounded features known as lenticulae, meaning small freckles or spots, suggested warm ice rising upward through the shell. Thermal infrared measurements detected localized surface temperatures too warm to be explained by weak sunlight alone. Different instruments, different methods, same answer. By the early 2000s, confidence among scientists had risen above 95% that Europa contains a vast liquid ocean beneath its crust. No drill had pierced the ice. No camera had seen the water directly. Yet the moon had revealed itself anyway, through gravity, magnetism, heat, and the slow movement of its frozen surface. The ocean remained hidden, but no longer invisible. Several kilometers beneath Europa's frozen crust, the ocean eventually meets stone, not ice again, rock, a planetary seafloor, buried under immense pressure, resting in darkness that has remained uninterrupted for billions of years. Down there, the weight of the ocean above may exceed 1,000 atmospheres, compressing everything into a slow and silent density. But the seafloor is not cold. Tidal forces continue working through Europa's interior, deforming the rocky mantle and releasing heat from within. Wherever heated rock comes into contact with salt water, circulation begins naturally. Water sinks into fractures, warms deep underground, dissolves minerals from surrounding rock, then rises back upward, carrying heat and chemistry with it. These systems are called hydrothermal vents. On Earth, hydrothermal vents were unknown until 1977, when the research submersible Alvin descended near the Galapagos Rift along the Pacific seafloor. Scientists expected volcanic rock, sediment, and little else. Sunlight never reaches those depths. The pressure is crushing. Temperatures near the vents exceed 400 degrees Celsius. Yet the seafloor was alive. Towering tube worms, nearly 2 meters long, clustered around black smoker vents, structures releasing dense clouds of mineral-rich water into the ocean. White crabs moved slowly across bacterial mats carpeting the rocks. Entire ecosystems flourished in complete darkness, isolated from sunlight entirely. The discovery overturned one of biology's oldest assumptions. Until then, scientists believed nearly all life ultimately depended on solar energy. Deep-sea ecosystems changed that understanding permanently. Organisms near the vents survive through chemosynthesis, a biological process where microbes extract energy from chemical reactions instead of light. Certain bacteria oxidize hydrogen sulfide from vent fluids, combining it with oxygen and converting the released energy into organic material. Life, it turned out, required chemistry more than sunlight. Europa may possess the same ingredients. Liquid water already appears strongly supported by magnetic measurements and surface activity. Internal heating provides a long-term energy source beneath the ocean floor. Spectroscopic observations of the reddish linea suggest salts and organic compounds may be present within material transported upward from below the crust. Another process may matter even more. When seawater interacts with certain hot rocks rich in iron and magnesium, a chemical reaction called serpentinization can occur. In simple terms, the rock changes structure as water enters it, producing molecular hydrogen in the process. On Earth, many vent microbes depend on hydrogen as fuel for metabolism. Models developed at NASA's Jet Propulsion Laboratory suggest Europa's mantle could support extensive serpentinization over geological timescales. If hydrothermal circulation exists there, hydrogen production may have continued steadily for billions of years beneath the ice. The comparison to Earth's deep oceans is no longer symbolic. The pressure ranges overlap. The mineral chemistry aligns. Darkness dominates both environments completely. Thermal gradients, meaning differences in heat that drive chemical movement, may also exist in remarkably similar forms. Even the likely energy pathways resemble one another closely. On our planet, hydrothermal vents support some of the densest biological communities in the oceans. Not despite the darkness, but because of the chemistry emerging from it. Europa's seafloor may function according to the same quiet logic, hidden beneath kilometers of black water and ice, untouched by sunlight, yet still potentially alive with energy moving through stone and salt. Against the enormous brightness of Jupiter, Europa sometimes appears as a tiny black silhouette drifting across the planet's cloud tops. In December of 2012, astronomers used that alignment carefully, turning the Hubble Space Telescope toward the Moon while Jupiter acted as a glowing backdrop behind it. The goal was subtle: detect anything extending beyond Europa's thin atmosphere. At first, the signal looked uncertain. A faint shape appeared near the southern hemisphere, barely visible against the reflected light from Jupiter below. It extended upward nearly 200 kilometers into space before fading into darkness. The structure resembled a plume, thin and diffuse, rising above the icy surface. The source was water vapor. Something beneath Europa's crust had forced material upward through fractures in the ice and expelled it directly into space. After billions of years sealed beneath kilometers of frozen crust, part of the hidden ocean had briefly touched the vacuum of the solar system. The discovery was published in the journal Science during December of 2013, but extraordinary claims demand repetition. Astronomers continued watching Europa carefully over the following years, searching for the same feature again. In 2016, Hubble detected the plumes once more. The location matched, the geometry aligned, the activity was real. For planetary science, the implications changed almost immediately. Until then, studying Europa's ocean seemed to require impossible engineering. Deep drilling through ice, perhaps tens of kilometers thick, or landing systems capable of surviving intense radiation for extended periods. But the plumes altered the problem entirely. Europa was bringing samples upward by itself. A spacecraft passing through one of these eruptions could collect ocean material directly without landing, drilling, or touching the surface at all. Tiny particles frozen within the vapor could reveal the chemistry of water hidden far below the crust. Salinity levels, acidity, organic molecules, potential energy sources, perhaps even subtle biological signatures. Scientists already had a precedent for this approach. At Saturn, the Cassini spacecraft repeatedly flew through the plumes erupting from another icy moon, Enceladus. Each pass allowed onboard instruments to analyze particles from its subsurface ocean in extraordinary detail. Over time, the findings transformed astrobiology. Cassini detected molecular hydrogen, strongly suggesting hydrothermal activity beneath Enceladus's seafloor. It identified complex organic compounds containing carbon chains far larger than expected from simple chemistry alone. Silica nanoparticles, microscopic mineral grains formed only in high-temperature water-rock interactions, indicated active vent systems deep below the crust. Then came phosphorus. In 2023, researchers reanalyzed archived Cassini data and confirmed phosphorus compounds within Enceladus's ocean material. Every known living organism on Earth depends on phosphorus. It forms part of DNA and RNA structures and helps store cellular energy through molecules like ATP. Enceladus is small. Europa is not. Europa contains roughly 3 times more liquid water than all of Earth's oceans combined. If plume activity there behaves similarly, the scientific opportunity becomes extraordinary. The same sampling strategy used successfully at Enceladus can operate at Jupiter as well. And this time, the instruments were designed specifically for that purpose from the beginning, waiting to pass through frozen ocean spray, moving silently above Europa's surface. Ice behaves differently when it exists under pressure for millions of years. On human timescales, frozen water seems rigid and motionless. But deep inside large planetary bodies, ice can flow slowly, bend gradually, and circulate like an extremely cold liquid. Europa's outer shell is not fixed in place. It moves continuously, though far too slowly for the eye to notice. The shell itself may average between 15 and 25 kilometers thick, but measurements suggest the thickness varies dramatically across the Moon. Some regions could be as thin as 3 kilometers. Others may descend beyond 30. This unevenness matters because the shell is not merely covering the ocean below. It is interacting with it. Scientists believe Europa's crust convects over geological time. Convection means warm material rises while cooler material sinks, creating a slow circulation cycle driven by differences in temperature and density. Near the hidden ocean, warmer ice becomes softer and more buoyant, gradually rising upward through the shell. Near the surface, colder ice grows denser and sinks back downward. One complete cycle may require between 30 million and 100 million years. The surface preserves traces of this movement everywhere. Among the most striking regions is Connemara Chaos, an area approximately 70 by 100 kilometers across. From orbit, it resembles shattered sea ice, frozen mid-collision. Large plates of crust appear broken apart, rotated, shifted sideways, and locked back together in new arrangements. Scientists realized the fragments could be matched together almost perfectly, like pieces from a cracked ceramic plate. The terrain was once continuous. Something below disrupted it, lifted it, and allowed it to refreeze before the geometry vanished completely. The process likely required warm ice or even liquid water to rise within only a few kilometers of the surface. Elsewhere, across Europa, rounded domes called lenticulae interrupt the plains. The word means freckles in Latin. These features form when warmer ice rises from below and gently pushes upward against colder layers above it. The shell deforms, but does not necessarily rupture completely. The effect resembles blobs moving inside a lava lamp, except the temperatures involved remain far below freezing. But the most important consequence of convection may not be geological at all. Europa's surface is constantly bombarded by energetic particles trapped within Jupiter's magnetic environment. These particles strike surface ice and trigger radiation chemistry, splitting water molecules apart and producing oxidants, chemically reactive compounds, including hydrogen peroxide, oxygen, and sulfur-bearing molecules. Those oxidants accumulate near the surface over time. If convection carries them downward into the ocean, they become available as chemical fuel. Meanwhile, hydrothermal systems below the seafloor may supply reduced compounds rising upward from the mantle. Reduced chemicals contain stored energy because they can react with oxidants. On Earth, ecosystems thrive where these opposite chemical states meet. Europa may possess both simultaneously. Energy from below, oxidants from above. The shell, therefore, becomes more than a frozen barrier between ocean and space. It acts as a transport system, cycling material downward and upward across immense spans of time. Chemicals produced under radiation at the surface may eventually mix into dark ocean water below, while minerals and salts from the ocean slowly work their way back toward the crust. The machine never stops moving. Around Jupiter, space itself becomes dangerous. The giant planet's magnetic field traps enormous numbers of charged particles released from the sun and from volcanic material erupting off nearby moons. Electrons and ions accelerate through the Jovian system at extraordinary speeds, spiraling along magnetic field lines and striking anything caught within their path. Europa orbits directly inside this region, immersed continuously in radiation intense enough to reshape chemistry at the atomic level. For humans, the surface would be unsurvivable. Radiation exposure on Europa averages approximately 5,400 millisieverts each day. By comparison, a chest X-ray delivers roughly 1/10 of a millisievert. Acute radiation sickness begins after much larger exposures, and doses near 4,000 millisieverts received over a short period are frequently fatal. Europa's surface exceeds that threshold in less than 24 hours. Even machines struggle there. Europa Clipper avoids orbiting the moon directly because prolonged exposure inside the radiation belts would steadily destroy its electronics. Instead, the spacecraft will orbit Jupiter itself and perform 49 rapid flybys of Europa, limiting accumulated damage during each pass. Timing becomes a form of survival. The spacecraft also carries substantial shielding. Its most sensitive systems are sealed within a radiation vault constructed from thick aluminum walls weighing nearly 150 kilograms. The vault acts like armor around delicate electronics, reducing particle penetration enough for the mission to continue functioning through repeated encounters with Jupiter's magnetic environment. But the radiation does more than destroy. Every charged particle striking Europa's surface transfers energy into the ice. Water molecules fracture apart under bombardment, splitting into reactive fragments that recombine into entirely new compounds. Hydrogen peroxide forms. Molecular oxygen accumulates. Sulfur compounds appear through interactions involving material originating elsewhere in the Jovian system. These substances are oxidants. An oxidant is a molecule capable of accepting electrons during chemical reactions, releasing usable energy in the process. On Earth, oxygen serves as one of the most important oxidants in biology. Complex organisms depend on it because reactions involving oxygen release large amounts of energy efficiently. Europa's surface may therefore be manufacturing chemical fuel continuously. The oxidants produced through radiation chemistry remain trapped inside the upper ice layers at first, but the shell itself slowly circulates over geological timescales. Surface ice sinks downward while warmer material rises upward from below. If oxidant-rich ice eventually reaches the ocean, the chemistry of the water changes fundamentally. Energy begins arriving from above as well as below. Researchers at NASA's Jet Propulsion Laboratory have modeled this transport process extensively. Their calculations suggest oxidants may have accumulated and mixed into Europa's ocean for billions of years. The cumulative delivery could be immense, especially across an ocean older than most complex life on Earth. Some estimates go further. Several studies propose that oxidant input into Europa's ocean may approach levels comparable to the oxygen buildup associated with Earth's Great Oxidation Event approximately 2.4 billion years ago. That transition altered our planet permanently, enabling more energy-intensive forms of metabolism and eventually supporting multicellular organisms. Europa's radiation environment therefore creates a strange contradiction. Above the ice, the conditions are violently hostile, but beneath it, the same destructive forces may be quietly feeding chemistry capable of sustaining life for unimaginable spans of time. Long before any spacecraft approaches Europa's surface, lawyers, microbiologists, and planetary scientists begin arguing over something invisible: not radiation, not engineering, microbes. The concern became formal international law in 1967 with the Outer Space Treaty, an agreement eventually signed by more than 100 nations. Among its requirements is a principle called planetary protection, meaning countries must avoid harmful contamination of other worlds while also preventing extraterrestrial material from contaminating Earth in return. For Europa, those rules become unusually strict. NASA classifies missions using contamination categories based on scientific sensitivity and biological risk. Europa falls into Category 5, the highest level of concern in both directions. Forward contamination matters. Backward contamination matters too. The forward problem begins inside cleanrooms on Earth. Spacecraft are assembled in carefully controlled environments where dust, particles, and microbial contamination are reduced dramatically. Engineers wear protective suits. Air circulates through filtration systems constantly. Surfaces are sterilized repeatedly. But clean is not sterile. Some organisms survive conditions that seem almost impossible. Bacillus subtilis, a common bacterium found in soil, produces dormant spores capable of surviving years in the vacuum of space during laboratory experiments. Another microbe, Deinococcus radiodurans, withstands radiation doses thousands of times greater than what would kill a human being. Certain bacterial spores, recovered from ancient salt crystals, have revived after approximately 250 million years of dormancy, older than the dinosaurs, older than flowering plants. Life can wait. This creates a scientific nightmare for Europa exploration. If even one terrestrial organism survives the journey, reaches the ocean, and reproduces there, future discoveries become uncertain forever. Imagine detecting microbial life beneath Europa's crust decades later, only to realize the organism shares ancestry with contamination accidentally introduced from Earth. The question would become unanswerable. Did we discover alien life, or merely transport our own biology into a second ocean? There would be no reliable way to reverse the mistake. The contamination would spread through a system isolated for billions of years, permanently altering the most important astrobiological investigation humanity has ever attempted. But contamination fear also points the opposite direction. Suppose a future mission returns samples from Europa's ocean to Earth. What if living organisms exist inside that material? Most astrobiologists believe the probability of a Europan microbe surviving terrestrial conditions is extremely low. The chemistry may differ too greatly. The environmental pressures, temperatures, and nutrient systems may be incompatible with Earth's biosphere. But low probability is not zero probability. And scientific caution exists precisely because consequences matter more than likelihood in certain situations. An unfamiliar microorganism interacting with Earth's ecosystems represents a risk impossible to fully test beforehand. Even if the danger proved minimal, the uncertainty alone forces governments and space agencies to proceed carefully. This is why planetary protection offices exist at all. The concern became so serious that NASA made a final decision regarding the Galileo spacecraft itself. After completing its mission in 2003, engineers intentionally directed the probe into Jupiter's atmosphere, destroying it completely. They feared that leaving Galileo uncontrolled might eventually allow orbital drift to send it crashing into Europa accidentally. The spacecraft burned apart inside Jupiter instead. A machine built to study the moon was deliberately sacrificed so that nothing from Earth would touch the ocean waiting beneath the ice. Most people imagine fear in physical terms: teeth, predators, infection, something emerging from darkness with hostile intent. But when planetary scientists speak carefully about Europa, the anxiety they describe is different. Abstract at first, then deeply unsettling once you follow the logic all the way through. The concern is not the organism itself. No serious researcher expects intelligent creatures beneath Europa's crust, and no one believes microbes hidden inside a dark ocean pose immediate danger in the cinematic sense. The terror comes from implication. One discovery leading inevitably into another, each conclusion narrowing the possibilities for what kind of universe we inhabit. Begin with the first step. If life exists inside Europa's ocean, it almost certainly originated independently from Earth. The Moon has remained isolated beneath kilometers of ice for roughly 4 billion years. There is no plausible pathway for continuous biological exchange between Europa and our planet across that span of time. That matters enormously. At present, Earth provides the only confirmed example of life anywhere in the universe. With a sample size of 1, scientists cannot determine whether biology is common or unimaginably rare. Perhaps life emerges naturally whenever chemistry becomes sufficiently complex. Or perhaps Earth represents an accident so improbable it occurred only once across billions of galaxies. Europa may answer that uncertainty directly. 2 separate origins of life inside one solar system would imply that biology is not exceptional. It would suggest that when liquid water, energy, and chemistry coexist long enough, living systems tend to appear. Life would become less like a miracle and more like a process, and the implications would continue expanding outward. If dark oceans beneath icy crusts can support biology, then habitable environments may exist far beyond narrow regions surrounding stars. Gas giants throughout the galaxy likely possess moons. Many may experience tidal heating similar to Europa's. Some may contain buried oceans persisting for billions of years. The number of potentially inhabited worlds could rise dramatically. But then another problem emerges immediately. Physicist Enrico Fermi famously asked a deceptively simple question in 1950. If intelligent life should be widespread across the galaxy, where is everybody? The Milky Way contains hundreds of billions of stars and is more than 13 billion years old. Even slow interstellar expansion should eventually leave visible traces somewhere. Yet the universe appears silent. No confirmed signals, no probes, no detectable engineering on cosmic scales. Nothing unmistakably artificial has ever been observed beyond Earth. This contradiction became known as the Fermi Paradox, meaning the conflict between high probabilities for extraterrestrial life and the complete absence of evidence. Europa intensifies that paradox. If life forms easily, then something else must prevent civilizations from surviving long enough to spread across the galaxy visibly. Cosmologists call this possibility the Great Filter, a barrier somewhere between simple chemistry and advanced interstellar societies. And if Europa contains life, the filter may not lie behind us. It may lie ahead. Perhaps civilizations routinely destroy themselves. Perhaps technological intelligence carries unavoidable risks. Perhaps there exists some pressure, event, or limitation that most species never survive long term. Europa cannot answer which possibility is correct, but a second genesis within our own solar system would make the silence harder to dismiss. This is the real source of the fear. Finding life beneath Europa's ice would be extraordinary proof that we are not alone. At the same time, it might also suggest that something happens to life almost everywhere eventually. The scientists pursuing this knowledge understand both conclusions clearly. They continue anyway. One afternoon in 1950, During lunch at Los Alamos National Laboratory, physicist Enrico Fermi interrupted a casual conversation with a question so simple that it still unsettles cosmology today. If intelligent life should exist throughout the galaxy, where is everybody? No one at the table could answer him. The numbers make the silence difficult to ignore. The Milky Way contains somewhere between 200 and 400 billion stars. Many of those stars are older than the Sun by billions of years. Modern exoplanet surveys now suggest planets are common rather than exceptional. Rocky worlds appear everywhere we look, and time is abundant. Even traveling far below the speed of light, a civilization capable of sustained spaceflight could spread gradually across the galaxy within 10 to 100 million years. Against the Milky Way's age of roughly 13.6 billion years, that interval is tiny, a brief moment. Cosmically speaking, it should have happened many times already. Yet the sky remains quiet. No confirmed transmissions from alien civilizations have ever been detected. No probes have arrived in our solar system. Astronomers searching for megastructures, gigantic engineering projects built around stars, have found nothing definitive. Humanity has listened for decades through radio telescopes and sent signals outward in return. Still, nothing. This contradiction became known as the Fermi Paradox, not a philosophical thought experiment, but an observable mismatch between probability and evidence. Based on the size and age of the galaxy, intelligent life should appear common. Based on observations, it appears absent. In 1998, economist Robin Hanson proposed one possible explanation. He called it the Great Filter. The idea is unsettlingly direct. Somewhere between lifeless chemistry and galaxy-spanning civilizations exists a stage that almost nothing survives, a bottleneck, one step so improbable or destructive that nearly every lineage fails there permanently. The filter may already lie behind us. Perhaps the origin of life itself is extraordinarily rare, requiring conditions so specific that it occurs only once per galaxy over immense spans of time. Perhaps simple microbial organisms are common, but the evolution of complex eukaryotic cells, cells containing internal structures like nuclei, represents the truly difficult leap. On Earth, that transition required nearly 2 billion years. Even later stages may matter. The Cambrian explosion, approximately 541 million years ago, produced a sudden expansion of complex body plans unlike anything earlier in Earth's history. Maybe that transformation depended on unlikely combinations of chemistry, oxygen, climate, and chance events, rarely repeated elsewhere. But the filter may also lie ahead. Technological civilizations acquire dangerous capabilities quickly. Nuclear arsenals, engineered pathogens, artificial intelligence systems operating beyond human oversight, environmental destabilization on planetary scales. Humanity now possesses multiple ways to damage its own long-term survival. And if most civilizations eventually fail after reaching technological maturity, the silence surrounding us begins to make sense. Europa, therefore, becomes more than an astrobiology mission. It becomes evidence in a much larger calculation. A sterile ocean would support the possibility that life itself is difficult to begin. We may already have passed the rarest stage. But if Europa contains independent life, then biology may emerge naturally whenever conditions allow. In that case, the silence means something else entirely. For most of the 20th century, Saturn's moon Enceladus attracted little attention. It appeared small, bright, and heavily frozen. only about 504 kilometers across. Smaller than the state of Arizona. Too small, many researchers assumed, to retain enough internal heat for long-term geological activity. Then Cassini arrived. The spacecraft entered Saturn orbit in 2004 and began surveying the system in detail. In 2005, its cameras captured something unexpected near Enceladus's south pole. 4 long fractures cut across the ice, running roughly parallel for more than 130 kilometers each. From those cracks, enormous plumes of water vapor and icy particles erupted continuously into space. Scientists nicknamed them the tiger stripes. The discovery changed Enceladus immediately from a frozen relic into an active ocean world. Cassini adjusted its mission repeatedly afterward, flying directly through the Plumes 22 separate times over the following years. With every pass, instruments collected microscopic particles and analyzed their chemistry in real time. The results became increasingly difficult to dismiss. Water vapor and ice grains confirmed that liquid reservoirs existed beneath the crust. Sodium chloride, ordinary table salt, appeared inside the ejected particles, indicating prolonged contact between water and rocky material below the seafloor. This mattered because interactions between rock and water create chemical gradients capable of storing energy. Then Cassini detected silica nanoparticles. These tiny mineral grains remain stable only under very specific conditions, usually when hot water exceeding 90 degrees Celsius interacts directly with rock before cooling rapidly. Their presence strongly implied active hydrothermal systems deep beneath Enceladus's ocean floor. Another signal followed. The spacecraft identified molecular hydrogen within the plumes, likely generated through water-rock reactions similar to serpentinization processes already studied on Earth. Many microorganisms near terrestrial hydrothermal vents consume hydrogen metabolically, using it as an energy source in environments completely isolated from sunlight. But perhaps the most provocative discoveries involved carbon chemistry. Cassini detected complex organic molecules with masses greater than 200 atomic units, structures far larger and more organized than simple contamination models predicted. These compounds drifted outward from an ocean hidden beneath kilometers of ice. Then, years after the mission ended, researchers revisited archived data once again. In 2023, a reanalysis published in the journal Nature confirmed phosphorus compounds inside plume particles from Enceladus. Phosphorus is not biologically optional on Earth. DNA depends on it. RNA depends on it. ATP, the molecule every known organism uses to transfer energy between cells, also depends on phosphorus chemistry. The implication was profound. Enceladus now possessed confirmed liquid water, internal heat, organic chemistry, hydrothermal activity, and all 6 elements considered essential for life as we understand it: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. And yet, Enceladus is relatively small. Europa contains far more water, experiences stronger tidal energy input, and may have maintained stable ocean conditions for longer spans of time. The discoveries at Saturn therefore transformed how scientists viewed Jupiter's moon. Enceladus proved that hidden ocean worlds could remain chemically active and surprisingly complex. Before Cassini, subsurface oceans seemed speculative and distant. After Cassini, they became places where biology no longer felt impossible. Europa remained larger, older, and in many ways even more compelling. At this moment, somewhere beyond the orbit of Mars, a robotic spacecraft is crossing interplanetary space in silence. No crew moves through its corridors because there are no corridors. No windows face the stars. Inside the machine, computers cycle steadily through commands while antennas remain pointed toward Earth across hundreds of millions of kilometers. Europa Clipper is already on its way. The spacecraft launched on October 14th, 2024, aboard a Falcon Heavy rocket from Kennedy Space Center in Florida. After leaving Earth, it began a journey expected to last approximately 5.5 years, covering nearly 2.9 billion kilometers before reaching Jupiter in April of 2030. The mission cost approaches $5 billion. That makes Europa Clipper the most expensive planetary science mission NASA has ever undertaken. The scale reflects the difficulty of the target. Jupiter's environment damages electronics relentlessly. Communication delays stretch close to an hour round trip, and Europa itself remains hidden beneath thick ice inside one of the harshest radiation regions in the solar system. Because of that radiation, Clipper cannot orbit Europa directly. Instead, the spacecraft will orbit Jupiter and perform 49 carefully planned flybys of the Moon. Some passes will approach within only 25 kilometers of the surface before Clipper swings away again, limiting cumulative radiation exposure while still allowing detailed observations. Every flyby serves multiple purposes simultaneously. One instrument, called RESON, short for Radar for Europa Assessment and Sounding, ocean to near surface, will send radio waves through the ice shell. By measuring returning echoes, scientists can estimate ice thickness, identify buried water pockets, and map the boundary where solid ice gives way to ocean below. Under ideal conditions, the radar may penetrate as deep as 30 kilometers. Another instrument, MASSPEX, meaning mass spectrometer for planetary exploration, will analyze gases and particles surrounding Europa with extraordinary sensitivity. Mass spectrometers identify molecules by measuring their mass and electrical charge. Mass specs may detect amino acids, organic compounds, and subtle chemical patterns associated with biology. SUDA, the surface dust analyzer, focuses on tiny ice and dust grains ejected from the surface or released through plumes. Each microscopic particle carries information about the environment from which it originated. Temperature matters too. THEMIS, a thermal imaging system, can identify heat differences smaller than a single degree, revealing recently active regions beneath the crust. MISE, the Mapping Imaging Spectrometer for Europa, studies reflected infrared light to distinguish salts, organics, water ice, and radiation-altered compounds across the Moon's surface. Meanwhile, the onboard magnetometer will measure Europa's induced magnetic field in far greater detail than Galileo achieved decades earlier, refining estimates of ocean depth, salinity, and structure. Another instrument watches for plumes directly. The ultraviolet spectrograph searches for faint columns of water vapor erupting above the surface, measuring their composition and behavior during close passes. If active plumes appear during a flyby, MASSPEX and SUDA together may achieve something remarkable. They could detect amino acid homochirality. Homochirality means molecules overwhelmingly prefer one mirror image form over another. On Earth, life uses almost exclusively left-handed amino acids. Non-biological chemistry usually produces equal mixtures of both forms. A single pass through the right plume could therefore reveal one of the clearest biosignatures ever measured beyond Earth. Inside a stream of numbers transmitted across hundreds of millions of kilometers, scientists are searching for patterns that geology cannot easily imitate. That is the central challenge of biosignatures. Not finding creatures, not hearing signals, finding chemistry that behaves in ways strongly associated with life. The difficulty is subtle. Rocks produce organic molecules naturally. Hydrothermal systems generate methane without biology. Even amino acids, the building blocks of proteins, form through non-living chemistry under certain conditions. A biosignature, therefore, cannot be merely interesting chemistry. It must represent an imbalance, a structure, or a pattern, difficult to explain without metabolism, operating somewhere beneath the ice. One of the strongest signals involves molecular handedness. Amino acids exist in two mirror image forms called enantiomers, meaning molecules with identical chemistry but opposite spatial arrangement, like left and right hands. Non-biological processes generally produce equal quantities of both forms. Chemists call this a racemic mixture. Life on Earth does something unusual. Every known organism uses almost exclusively left-handed amino acids when building proteins. The consistency is extraordinary across bacteria, plants, animals, and fungi alike. If Europa's ocean material showed a strong preference for one-handedness over the other, especially left-handed dominance with only trace amounts of right-handed forms, the result would be difficult to attribute to random chemistry alone. Mass spectrometers can measure this directly. Another category involves isotopes. Isotopes are versions of the same element containing different numbers of neutrons, giving them slightly different masses. Living organisms often process lighter isotopes more efficiently because lighter atoms participate in reactions more easily. Over time, biology leaves fingerprints in surrounding material. Carbon-based life on Earth tends to favor carbon-12 over carbon-13. Sulfur-metabolizing organisms similarly prefer sulfur-32 relative to sulfur-34. These biases create measurable isotopic fractionation, meaning chemical reservoirs become depleted in heavier isotopes compared with expected geological values. Such signatures can persist long after organisms disappear. Complex molecular structures also matter. Certain compounds exist in nature primarily because biology assembles them repeatedly. Fatty acids help construct cell membranes. Porphyrins form the molecular core of chlorophyll and hemoglobin. Nucleobases store genetic information within DNA and RNA. Geology can sometimes produce fragments of these molecules, but biology tends to create them in concentrated, organized distributions rather than dilute random assortments. Detecting large quantities of structurally specific organics in plume material would therefore attract immediate attention. Gas chemistry provides another clue. On Earth, ancient microorganisms called methanogenic archaea release methane through metabolism. Hydrothermal systems can also generate methane abiotically, meaning without life. Scientists therefore compare observed gas concentrations against theoretical geological production rates. If Europa produces substantially more methane or hydrogen than water, rock chemistry alone predicts, the excess may indicate biological activity contributing additional reactions. But no single biosignature is considered definitive by itself. One anomaly might reflect contamination, measurement error, or an unfamiliar geological process. Multiple independent signatures appearing together become much harder to dismiss. Left-handed amino acids combined with isotopic fractionation, unusual gas ratios, and concentrated complex organics would point repeatedly toward the same conclusion. Not proof beyond all doubt, but something very close to it, arriving quietly through data collected during a brief passage through frozen spray above a distant ocean. Long before any machine reaches Europa's ocean, another machine must first survive the surface. Europa Clipper will identify promising regions, map the ice shell, and search for chemical traces drifting above the moon. But its instruments remain distant from the ocean itself. They study reflections, particles, magnetic fields, and frozen material carried upward through fractures. Eventually, scientists will want direct contact. NASA has studied Europa lander concepts since the early 2000s, refining designs around one central problem: how to perform meaningful biology experiments before radiation destroys the spacecraft. In a 2016 Science Definition Team report, researchers outlined the minimum requirements needed for a successful mission. The lander would need to survive approximately 20 days. That brief operational window reflects the brutality of Europa's radiation environment. Even heavily shielded electronics degrade steadily beneath Jupiter's particle bombardment. Every hour on the surface matters. The lander must also dig. Samples collected directly from exposed surface ice may already be chemically altered by radiation processing, meaning high-energy particles have broken apart or modified delicate organic compounds over time. To avoid this, the spacecraft would need to reach at least 10 centimeters below the surface before analyzing material. Beneath that shallow depth, possible biosignatures stand a better chance of remaining intact. Inside the lander, miniature laboratories would search for amino acids, isotope ratios, and complex organics directly within the ice. All of this must occur autonomously because communication delays between Earth and Jupiter range from roughly 35 to 52 minutes each way. No human could guide the landing in real time. That creates another difficulty. Europa has no GPS network, no high-resolution landing maps at meter scale, and no certainty regarding terrain stability. The most scientifically valuable regions are geologically young and recently active, exactly the places most likely to contain fractures, ridges, or unstable ice blocks. The spacecraft therefore must land blind, think independently, and adapt instantly. Even then, a lander only scratches the surface. The more ambitious concept comes afterward, a cryobot. The name combines cryo, meaning cold, with robot. Engineers imagine a nuclear-powered probe carrying a heated nose cone capable of slowly melting downward through kilometers of ice over several years. Behind it, the tunnel would begin refreezing almost immediately. To remain connected with the surface, the cryobot would unspool a communication tether carrying power and data through the narrowing melt channel. At the base of the ice shell, the probe would release a small autonomous submarine into an ocean no instrument has ever entered. Everything about this mission remains difficult. The ice may vary dramatically in density, salinity, and temperature across different layers. Meltwater could refreeze unevenly around the tether. Mineral impurities might interfere with heat transfer. Pressure conditions at the ocean boundary remain uncertain. And throughout the descent, the system would operate largely alone. Some engineers estimate such a mission remains 30 to 50 years away from technical feasibility. Others believe rapid advances in robotics, autonomous navigation, and compact nuclear systems may shorten that timeline considerably. But even optimistic projections acknowledge the scale of the challenge. Reaching Europa's ocean means building a machine capable of descending through an alien cryosphere for years without rescue, maintenance, or direct human control, carrying humanity's first attempt to touch a second ocean world directly. Every search for extraterrestrial life begins with a hidden assumption. We assume life elsewhere resembles life here closely enough for us to recognize it when we see it. That assumption shapes every instrument aboard Europa Clipper, every biosignature definition, and every laboratory experiment designed to interpret incoming data. But what if the assumption is incomplete? Life on Earth stores information using DNA and RNA. It builds proteins from 20 specific amino acids. It uses water as a solvent, meaning the liquid medium where chemistry occurs inside cells. Nearly every organism also relies on ATP, adenosine triphosphate, as a universal energy transfer molecule. These systems appear remarkably consistent across all known biology. Yet consistency does not necessarily mean inevitability. It may simply reflect shared ancestry. Every organism on Earth descended from earlier organisms already using the same molecular toolkit. Evolution modifies existing chemistry more easily than inventing entirely new systems from nothing. Astrobiologists, therefore, ask a difficult question. Are carbon-based cells suspended in water universal requirements for life, or merely one successful solution among many possible biochemical arrangements? The debate remains active because science currently possesses only one confirmed example of living chemistry: ourselves. Several alternatives have been explored seriously in laboratories and theoretical models. One possibility involves different solvents. Ammonia, for instance, remains liquid at temperatures far colder than water's freezing point. In extremely cold environments, ammonia-based biochemistry might permit slower but still functional metabolic reactions. Other researchers study alternative genetic molecules. TNA, meaning threose nucleic acid, and PNA, peptide nucleic acid, can both store genetic information and replicate under laboratory conditions. Some scientists suspect such molecules may even have preceded DNA during Earth's earliest biochemical stages before more stable systems evolved. A different world might never transition beyond them. The amino acid question remains equally open. Earth life relies heavily on 20 amino acids when constructing proteins, yet meteorites and laboratory simulations reveal hundreds of amino acids occurring naturally throughout chemistry. Another biosphere could theoretically select an entirely different molecular alphabet while still producing functional biology. Even silicon receives occasional attention. Silicon sits directly beneath carbon on the periodic table and forms long molecular chains under some conditions. Carbon remains chemically superior because it bonds more flexibly and stably across wider environments. But in carbon-poor regions with abundant silicon, unfamiliar biochemical pathways might emerge. Most scientists still consider truly alien chemistry unlikely on Europa specifically. The Moon appears to contain liquid water, carbon compounds, salts, and familiar elements associated with terrestrial oceans. These similarities make Earth like biochemistry, the leading expectation. But expectation is not certainty. 4 billion years of isolated evolution leave enormous room for divergence. If European organisms use unfamiliar amino acids, different genetic systems, or metabolic reactions outside our current detection models, instruments may interpret the resulting chemistry as merely strange geology. A living ecosystem could therefore appear sterile because it fails to match patterns. Earth scientists were trained to recognize this limitation cannot be engineered away completely. When Europa Clipper eventually samples plume material, every result will pass through definitions created by one species studying itself from a single planet. If nothing recognizable appears in the data, the conclusion remains narrower than many people realize. Not that nothing lives there, only that nothing matching our present understanding announced itself clearly enough for us to notice. Across Europa's frozen surface, long reddish fractures stretch for thousands of kilometers like scars crossing pale ice. Some remain narrow and delicate. Others widen into chaotic bands, where the crust appears torn apart and reassembled. For decades, planetary scientists studied those markings without fully agreeing on what they were actually seeing. The answer depended on light. Spectroscopy, the technique used to study Europa remotely, works by separating reflected light into precise wavelengths. Different chemicals absorb and reflect specific portions of the spectrum, creating identifiable patterns often compared to barcodes. By matching those patterns against laboratory measurements on Earth, researchers can infer surface composition from enormous distances. Europa's spectra proved frustratingly ambiguous. Early observations from ground-based telescopes, the Hubble Space Telescope, and the Galileo mission suggested compounds rich in sulfur. Magnesium sulfate and sulfuric acid hydrates became leading explanations because Jupiter's environment contains abundant sulfur particles, many originating from volcanic eruptions on the nearby moon Io. The interpretations seemed reasonable for years, but the data never fit perfectly. Some spectral features remained difficult to explain, particularly within younger regions where material from deeper layers appeared exposed more recently. Scientists suspected the lineae might contain ocean-derived compounds altered further by radiation after reaching the surface. Then the picture shifted. In 2019, a research team led by Samantha Trumbo at the California Institute of Technology used Hubble's ultraviolet spectrograph to analyze Europa with greater sensitivity. The observations identified sodium chloride across portions of the surface, ordinary table salt. The discovery, published in Science Advances, represented the first direct detection of a specific ocean-related salt on Europa. Sodium chloride matters because it dominates Earth's oceans chemically. Its presence suggests Europa's subsurface water interacts extensively with rock, dissolving minerals and circulating through geochemical systems broadly similar to terrestrial seawater environments. That similarity carries implications. Salt chemistry influences acidity, electrical conductivity, and mineral transport inside oceans. Europa's apparent sodium chloride concentrations imply a pH range and ionic composition potentially compatible with Earth-like biochemistry. Just as importantly, the finding confirms that material from the hidden ocean reaches the surface through fractures, convection, or eruptive processes. The ocean is not sealed completely away, but the color itself remains unresolved. Pure sodium chloride is white. Europa's lineae are not. They range from rust-colored streaks to deep reddish-brown regions, concentrated along fractures and disrupted terrain. Something else modifies the chemistry after exposure to Jupiter's radiation environment. Several possibilities remain under investigation. Radiation may alter organic compounds rising from below, darkening them chemically over time. Laboratory experiments also show irradiated sodium chloride can produce metallic sodium, which then reacts rapidly with surrounding compounds to create colored residues. Sulfur particles from Io continue to complicate the picture as well, coating portions of Europa's surface continuously. The distinction matters more than appearance alone suggests. If the color results primarily from irradiated ocean organics, the lineae may preserve chemical traces connected indirectly to biological activity. If radiation and sulfur chemistry alone explain everything, the implications become less dramatic. Europa Clipper's MISE instrument, the Mapping Imaging Spectrometer for Europa, will examine the Moon at approximately 25 times the compositional resolution achieved previously. For the first time, scientists may map individual chemical environments across the fractures in detail, fine enough to separate radiation effects from deeper ocean chemistry clearly. And hidden within those colors, the ocean may already be speaking. For years, Europa existed less as a mission than as a recurring argument. Scientists wanted to go. Engineers believed it was possible. But between curiosity and launch stood the machinery of budgets, politics, competing priorities, and the simple reality that deep space exploration is extraordinarily expensive. Again and again, Europa missions approached approval before disappearing quietly into cancellation notices and unfinished studies. The first major attempt emerged during the early 2000s. NASA proposed the Jupiter Icy Moons Orbiter, a nuclear-powered spacecraft intended to study Europa, Ganymede, and Callisto sequentially. The design depended on advanced nuclear propulsion systems capable of supplying long-term electrical power far from the Sun. On paper, the mission promised unprecedented access to the Jovian system, but the technology proved costly. Development expenses climbed while the United States government shifted focus toward the Vision for Space Exploration, a program prioritizing human return missions to the Moon after the Space Shuttle Columbia disaster. In 2005, Jupiter Icy Moons Orbiter was canceled before construction advanced significantly. Europa remained out of reach. A second effort followed several years later. Beginning around 2009, NASA and the European Space Agency developed a joint concept called the Europa-Jupiter System Mission. Under the proposal, multiple spacecraft would explore Jupiter's major moons cooperatively, sharing scientific responsibilities and financial burden. Then priorities shifted again. In 2011, the European Space Agency redirected attention toward JUICE, the Jupiter Icy Moons Explorer, focusing primarily on Ganymede rather than Europa. Without European cost-sharing, NASA struggled to justify the growing mission expense independently. The collaboration dissolved before launch approval. Once more, Europa disappeared from active development. But the most serious threat arrived afterward, not from engineering limitations but from paperwork. During several consecutive budget cycles, the White House Office of Management and Budget removed Europa mission funding entirely from NASA's proposed budgets. $0. Had those recommendations remained unchanged, Europa Clipper would never have been built. Instead, something unusual happened. Members of Congress repeatedly restored the funding during appropriations, negotiations, effectively overruling executive branch priorities. 4 years in succession during fiscal years 2014 through 2017. The persistence was remarkable. At a time of intense political polarization in Washington, Europa received bipartisan support from lawmakers representing very different ideological positions. Part of that support reflected scientific ambition. The possibility of discovering evidence for life beyond Earth carried obvious historical significance. But economics mattered too. NASA centers, aerospace contractors, and engineering firms connected to the mission spread across numerous congressional districts, creating jobs, infrastructure investment, and long-term technological development. Scientific curiosity and domestic industry aligned unusually well. Formal approval for Europa Clipper arrived in 2015. Full mission development accelerated by 2019. Against expectations, the spacecraft remained largely on schedule and within budget through completion. That alone surprised many observers. Meanwhile, Europe continued forward with JUICE, launched in April of 2023. The spacecraft will arrive at Jupiter in July 2031 and eventually enter orbit around Ganymede. For a period, both JUICE and Europa Clipper will operate within the Jovian system simultaneously, sharing observations across different moons. But there is another reality beneath the schedules and funding battles. For decades, humanity came very close to never looking closely at Europa at all. Long before Europa Clipper reaches Jupiter, scientists are already preparing for a different challenge entirely. Not how to detect possible biosignatures, but how to speak about them responsibly once they appear in the data. Because history has made them cautious. In Antarctica, during 1984, researchers recovered a meteorite, later designated ALH 84001. Nearly a decade afterward, scientists confirmed the rock originated from Mars after being blasted into space by an ancient impact before eventually falling to Earth. Then came the announcement. In 1996, a NASA team led by David McKay published a paper in the journal Science, arguing the meteorite might contain evidence of fossilized Martian microorganisms. The evidence included microscopic structures resembling bacterial shapes, magnetite crystals similar to those produced biologically on Earth, and carbon-rich compounds called polycyclic aromatic hydrocarbons. The reaction was immediate. President Bill Clinton addressed the discovery publicly from the White House. Newspapers across the world treated the possibility as historic. For a brief period, humanity seemed on the edge of confirming life beyond Earth for the first time. But the certainty faded quickly. As additional laboratories studied the meteorite, alternative explanations emerged for each observation. Non-biological geological processes could plausibly form the magnetite crystals. Chemical contamination complicated the carbon analysis. The tiny structures themselves remained ambiguous at the scales involved. No consensus formed. Even today, the claim remains unresolved scientifically, though most researchers no longer consider ALH 84001 persuasive evidence for life. Within astrobiology, the episode became a permanent cautionary example of how premature communication can distort both science and public understanding. Europa Clipper's science teams are determined not to repeat that sequence. If the spacecraft detects an unusual mass spectrum, meaning a chemical pattern inconsistent with expectations, the result will not trigger an immediate global announcement. Instead, scientists will first attempt replication through additional flybys targeting the same region repeatedly. Consistency matters enormously. One anomalous reading might reflect instrument noise, contamination, unexpected geology, or data processing errors. Multiple independent measurements strengthen confidence gradually. Teams not involved in the original detection will also analyze the raw information separately to reduce confirmation bias, meaning the tendency to interpret evidence in ways supporting prior expectations. Only after extensive internal review would peer-reviewed publication begin. That process alone may require months or even years. Scientific journals demand independent scrutiny, statistical validation, and detailed methodological transparency before extraordinary claims become accepted publicly. The threshold remains intentionally high. A false positive carries lasting consequences. Public trust in astrobiology could erode significantly after a major retraction, but the opposite possibility creates its own pressure. A genuine detection of extraterrestrial biology would permanently alter humanity's understanding of itself, making caution equally necessary in another direction. Interestingly, NASA has no formal written protocol describing exactly how confirmed extraterrestrial life would be announced. There are communication frameworks, media planning documents, and scientific review procedures, but no universal script exists because the evidence itself could arrive in forms impossible to predict beforehand. A biosignature might emerge gradually through years of accumulated data rather than a single dramatic moment. And somewhere within that uncertainty lies a strange reality. The first evidence that Earth is not biologically alone may appear first not as a headline, but as quiet disagreement among scientists studying numbers on computer screens late at night. Imagine an ocean older than forests, older than dinosaurs, older even than complex cells. Europa's hidden sea has likely remained liquid for roughly 4 billion years. Not intermittently, not through brief warming periods. Continuously, sustained by tidal forces beginning only a few 100 million years after Jupiter itself formed from the early solar nebula. That timescale changes everything. Earth is approximately 4.54 billion years old, the oldest widely accepted evidence for microbial life on our planet dates to around 3.7 billion years ago. But complex, multicellular organisms arrived astonishingly late by comparison. Animals, plants, and fungi emerged only within the last 600 million years. For most of Earth's history, life remained microscopic. Europa's ocean, therefore, may have existed in stable chemical conditions for longer than complex life has existed anywhere on Earth. If biology began there early, as it apparently did here, evolution inside that ocean would have proceeded independently across spans of time almost impossible for human intuition to grasp. And it would have done so in isolation. The ocean lies sealed beneath kilometers of ice. Meteor impacts cannot easily penetrate downward. Surface radiation remains largely blocked before reaching the water below. No seasons alter climate cycles. No sunlight enters the depths. Day and night have no meaning there because darkness never changes. Conditions may remain stable for millions of years at a time. Evolutionary pressures inside such an environment would differ profoundly from those shaping terrestrial ecosystems. On Earth, life constantly adapts to shifting weather, changing temperatures, volcanic disasters, asteroid impacts, and competition across countless habitats. Europa's ocean may instead experience immense environmental consistency, interrupted only occasionally by geological shifts deep beneath the seafloor. Energy would come entirely from chemistry. Hydrothermal systems likely inject mineral-rich fluids upward from the rocky mantle, while oxidants descend slowly from the ice above. Organisms, if they exist, would metabolize chemical gradients rather than sunlight. Photosynthesis, the process supporting nearly all large ecosystems on Earth, becomes impossible beneath Europa's ice shell. Pressure would shape life as well. Estimates suggest the seafloor may experience pressures around 1,300 atmospheres, far exceeding conditions within Earth's deepest trenches. Water behaves differently there. Ice phases become exotic. Mineral interactions change subtly under such compression. Biology would adapt accordingly. Some scientists suspect this stability might actually limit evolutionary complexity. In a predictable environment with steady chemical energy sources, simple microbial ecosystems may remain highly efficient indefinitely, without strong pressure toward larger multicellular forms. But there is another possibility. Competition itself drives innovation. 4 billion years of organisms struggling over chemical resources around hydrothermal systems could produce evolutionary experiments unlike anything Earth biology has encountered. Entire metabolic strategies may have emerged and vanished there long before multicellular animals appeared on our own planet. And no human framework currently predicts what prolonged isolated evolution under those conditions should eventually create. This uncertainty matters because Europa is not merely another potentially habitable environment. It represents a parallel biological experiment conducted separately from Earth across nearly the entire age of the solar system. A second history of life may have unfolded there in darkness, while our own biosphere transformed continents, filled oceans, and eventually developed minds capable of wondering what survived beneath distant ice. On a chalkboard in West Virginia, during the autumn of 1961, radio astronomer Frank Drake wrote 7 variables connected by multiplication signs. The symbols described star formation, planetary systems, biology, intelligence, and communication. Together, they formed what became known as the Drake equation. But the equation was never truly about arithmetic. It was a map of uncertainty. Each term represented a question humanity could not yet answer. How many stars possess planets? How many planets support life? How often does intelligence emerge? For decades, one variable overwhelmed all the others with ignorance, the fraction of worlds where biology actually begins. We had only Earth. A single example cannot reveal whether life is common or impossibly rare. It only proves the process happened once. For more than half a century, every estimate inside the equation rested partly on philosophy because there was no second biosphere to compare against. Europa changes that landscape completely. If life exists there, then biology emerged independently inside a buried ocean, separated from Earth for roughly 4 billion years. That would mean 2 origins of life occurred within a single solar system. The implication spreads outward immediately, altering how we think about habitable environments across the galaxy. The classical habitable zone becomes too narrow. Traditionally, astronomers defined habitability as a thin region around a star where liquid water can survive on a planetary surface. Too close and oceans evaporate. Too far and water freezes solid. Earth sits comfortably within that range. But Europa lies almost 778 million kilometers from the Sunday sunlight. There is weak, only about 1/25th the intensity reaching Earth. Surface temperatures average near minus 160 degrees Celsius. And yet beneath the ice, water remains liquid. The energy source is gravitational rather than solar. Orbital resonance continuously flexes Europa's interior, generating heat through tidal deformation. A moon does not need warm sunlight if gravity can keep an ocean alive from below. That realization expands the inventory of potentially habitable worlds enormously. Within our own solar system alone, scientists suspect subsurface oceans beneath Europa, Enceladus, Ganymede, Callisto, Titan, Triton, and perhaps even Pluto. Some estimates suggest these hidden oceans collectively contain more liquid water than all surface oceans on Earth combined. And our galaxy contains hundreds of billions of stars. Many possess gas giants. Gas giants frequently host moons. Some moons likely experience tidal heating similar to Europa's. Suddenly, the Milky Way appears filled not merely with planets, but with concealed oceans existing in darkness around distant worlds we cannot yet directly observe. The Drake equation shifts accordingly. If chemistry reliably produces life whenever stable liquid water and energy coexist, then the number of inhabited environments may rise from rare exceptions to staggering abundance. Civilizations capable of technology could number in the millions or beyond. But the contradiction deepens. We still detect nothing. No verified transmissions cross the sky. No ancient probes drift through the solar system. No unmistakable engineering signatures appear around distant stars. The silence remains absolute. And because of Europa, that silence no longer feels comfortably empty. Long before a spacecraft reaches Europa's ocean, we rehearse for it in silence beneath Antarctic ice, inside dark seawater, and among environments once considered completely hostile to biology. The search for alien life has become, in many ways, a journey deeper into Earth's own hidden regions. The most famous analog lies beneath Antarctica. Lake Vostok stretches roughly 250 kilometers long beneath 3.7 kilometers of ice. Buried below the East Antarctic ice sheet, it remained sealed from the atmosphere for somewhere between 15 and 25 million years. No sunlight reaches it, no winds disturb it. The water exists in permanent darkness beneath pressures hundreds of times greater than surface conditions. For decades, Russian scientists drilled cautiously downward. They stopped repeatedly, worried that drilling fluids or surface microbes might contaminate the lake forever. When the breakthrough finally came in 2012, water surged upward into the borehole and froze again in the cold shaft above. Inside that refrozen water, researchers identified genetic traces from approximately 3,500 microbial species. One bacterium showed less than 86% similarity to known organisms in existing databases, suggesting long isolated evolution beneath the ice. Not alien, but distant from us. Lake Vostok is smaller, younger, and chemically different from Europa's ocean. But it proved something essential. Isolation alone does not sterilize a world. Elsewhere in Antarctica, another analog challenges assumptions about temperature itself. Don Juan Pond appears shallow and unremarkable, yet it contains the saltiest natural water known on Earth. The salinity is so extreme that the pond remains liquid near -51 degrees Celsius. Almost every complex organism dies under those conditions. Microbial life survives anyway. These organisms are called halophiles, meaning salt lovers. Their cellular machinery evolved specifically to function where ordinary biology collapses. Proteins remain stable. Membranes continue operating. Metabolism persists slowly inside water that seems too cold and saline for life at all. But the strongest Europa comparison may lie beneath the Atlantic Ocean. In 2000, researchers discovered the Lost City hydrothermal field along the mid-Atlantic ridge. Towering carbonate structures rise from the seafloor there, some reaching 60 meters high. Warm, alkaline fluids vent continuously into the surrounding darkness. Unlike many hydrothermal systems, Lost City is not powered mainly by volcanism. Its chemistry comes from serpentinization, a reaction between seawater and mantle rock that releases hydrogen and methane. The same process is strongly suspected beneath Europa's seafloor. Entire microbial ecosystems at Lost City survive by consuming those chemicals directly. No sunlight participates at all. Then there is Blood Falls at Taylor Glacier, where iron-rich brine periodically seeps through Antarctic ice and stains the surface deep red. The trapped water below remained isolated for roughly 1.5 million years. Oxygen never enters. Light never penetrates. Yet microbial communities persist within it, metabolizing sulfur and iron compounds in total darkness. The red color appears when dissolved iron contacts oxygen at the surface and oxidizes. Each analog remains imperfect. Europa's ocean is older, deeper, colder, and more extreme than every environment we have explored on Earth. But these places quietly dismantled an assumption humanity carried for centuries: the idea that life requires gentle conditions to endure. A sealed ocean beneath Europa's ice may eventually force humanity into one of the deepest scientific questions ever asked, not simply whether life exists elsewhere, but whether life everywhere shares the same beginning. The concept has a name already: panspermia. The idea proposes that life, or at least microbial precursors of life, can travel naturally between worlds carried inside rock fragments blasted into space by asteroid impacts. What once sounded speculative has gradually moved into serious planetary science because meteorites from other planets already exist on Earth. And we have pieces of Mars in laboratories. Large impacts on Mars eject surface rock beyond the planet's gravity. Some fragments cross interplanetary space and eventually fall onto Earth. Scientists estimate that Earth and Mars exchange roughly 100 kilograms of rocky material each year through this process. Inside sufficiently thick rocks, microbes receive protection. Radiation weakens toward the interior. Temperatures remain relatively stable. Transit times occasionally become short enough for dormant spores to survive the journey. Laboratory experiments with Bacillus subtilis demonstrated that bacterial spores can endure simulated space conditions remarkably well when shielded within rock material. Life appears stubborn, but Europa complicates the equation enormously. The distance from Earth or Mars to Jupiter is vast compared with transfers inside the inner solar system. Radiation exposure grows harsher farther outward, especially near Jupiter's magnetic environment. Transit times may stretch across millions of years. Most researchers consider successful biological transfer to Europa unlikely. Not impossible, just difficult. The answer ultimately depends on chemistry. If organisms inside Europa's ocean use DNA or RNA, rely on the same genetic code, assemble proteins from the same 20 amino acids, and process energy through molecules resembling ATP, then shared ancestry becomes the strongest explanation. The odds of two separate biospheres, independently producing identical molecular systems, are extraordinarily low. That result would still transform science. Life spreading naturally between worlds would imply biology travels through planetary systems more readily than once imagined. A living cosmos might propagate itself through impacts, debris, and time. But another possibility waits beneath the ice. Europa's organisms may use different informational molecules entirely. Their genetics could rely on alternatives to DNA. Their proteins might employ unfamiliar amino acids. Their metabolism may transfer energy through chemistry Earth biology never developed. That would indicate a second genesis, an independent origin of life inside one solar system changes the statistical meaning of existence itself. Two unrelated biospheres around the same star would imply that biology emerges wherever conditions permit it, not as an impossibly rare accident, but as a natural outcome of chemistry and energy interacting over immense spans of time. The mathematics becomes overwhelming. If life began twice independently among the 8 major planets and their moons orbiting one ordinary star, then the galaxy is likely saturated with living systems beyond counting. Oceans, Atmospheres, ice shells, and hidden seas across the Milky Way may already contain biology unfolding quietly in darkness. And this conclusion would not emerge from philosophy. It would come from molecular structure measured directly by instruments crossing through frozen plumes above a distant moon. Tiny chemical asymmetries inside microscopic particles could reveal whether every living thing in the universe belongs to one ancestral tree, or whether nature builds life again and again whenever the conditions allow it. Deep beneath Europa's frozen surface, boundaries and structures wait in complete darkness, untouched by sunlight for billions of years. When Europa Clipper begins its close flybys in the early 2030s, one instrument will attempt to reveal that hidden landscape directly. The instrument is called RESON. Its full name is Radar for Europa Assessment and Sounding, Ocean to Near Surface. The purpose is simple to describe and extraordinarily difficult to achieve, transmitting radio waves through kilometers of alien ice and reconstructing what lies below from the returning echoes. The method resembles medical ultrasound, but instead of sound waves moving through tissue, RESON uses radio waves traveling through ice. When those waves encounter a boundary between different materials, part of the signal reflects backward toward the spacecraft. By measuring the timing and strength of those reflections, scientists can infer the depth and composition of buried structures. Europa's ice becomes partially transparent to radio energy. RESON operates using two frequencies simultaneously. The lower frequency, 9 MHz, penetrates deeply into the shell but produces coarser detail. The higher frequency, 60 MHz, offers sharper resolution while sacrificing penetration depth. Together, they create a balance between seeing far and seeing clearly. The strongest target is the ocean itself. Where solid ice transitions into liquid water, the physical properties change dramatically. Density, electrical conductivity, and molecular structure all shift at once. That boundary should generate a bright radar reflection extending across enormous distances beneath the crust. But scientists are searching for more than a single interface. Inside the shell may exist brine lenses, pockets of highly saline liquid trapped between colder ice layers. Because salty water responds differently to radio waves than solid ice, these regions should produce distinct signatures in the radar data. Such pockets matter enormously. They may represent intermediate habitats where ocean chemistry interacts more directly with the surface. Material moving upward or downward through the shell could temporarily collect there. A future lander might target those regions rather than drilling entirely through the ice. Chaos terrain is another priority. From orbit, places like Connemara Chaos appear shattered and rearranged, as though enormous ice plates fractured, shifted, and froze again. RESON may determine whether those disruptions formed above liquid reservoirs or through slow deformation of warm solid ice rising from below. The difference changes everything about accessibility. A shallow water reservoir, only a few kilometers beneath the surface, presents a vastly easier target for future exploration than an ocean buried beneath 20 kilometers of ice. The radar will also produce the first global thickness map of Europa's shell. Thin regions become prime landing sites. Thick regions reveal where heat flow is weaker or geological recycling slower. We already use similar systems on Earth. Ice-penetrating radar discovered Lake Vostok beneath Antarctica and later identified more than 400 subglacial lakes hidden under polar ice sheets. Aircraft surveys across Greenland routinely map glacier thickness and buried channels invisible from the surface. But Europa pushes the technology into another category entirely. Reason will perform these measurements from a spacecraft moving at several kilometers per second above a moon orbiting nearly 628 million kilometers from Earth. And from those faint returning echoes, we may finally begin seeing the architecture of an ocean no human eye has ever touched. Every instrument traveling toward Europa carries an invisible assumption inside it. The assumption is not mechanical. It is conceptual, built quietly into the entire search for extraterrestrial life long before the spacecraft ever launched. We search for life by searching for ourselves. Mass spectrometers look for amino acids because Earth biology uses them. Chemical models prioritize carbon compounds because every known organism on Earth is carbon-based. Biosignatures rely on isotope ratios, molecular asymmetry, and metabolic gases because those are the fingerprints life leaves here. But what if Earth is only one example among many possibilities? This concern has become increasingly important in philosophy of science and astrobiology. It is known as the reference class problem, the difficulty of defining a universal category from a sample size of one. Humanity possesses exactly one confirmed biosphere. From that single case, we attempt to infer the general rules governing all life everywhere in the universe. We do not yet know which features of terrestrial biology are unavoidable consequences of chemistry and which emerged through historical accident on the early Earth. Even familiar molecules become uncertain. All known proteins use left-handed amino acids almost exclusively. Right-handed forms exist naturally, yet biology largely ignores them. Scientists call this preference homochirality. It is among the strongest biosignatures because non-biological chemistry tends to produce equal mixtures of both orientations. But perhaps Europa's organisms would not care. An independently evolved biosphere might use both forms simultaneously, or even prefer the opposite orientation entirely. In that case, one of our clearest indicators of biology could disappear from the data completely. The same uncertainty surrounds carbon. Carbon forms stable, flexible molecular chains extremely well, making it ideal for complex chemistry. Most researchers suspect it remains the best foundation for life anywhere, but suspicion is not proof. Another environment might stabilize different molecular systems under pressures and temperatures unfamiliar to Earth biology. Water presents a similar dilemma. Europa almost certainly contains a water ocean, making Earth-style chemistry more plausible there than on worlds dominated by methane or ammonia. Yet we still cannot say with certainty that liquid water is the only solvent capable of supporting complex, self-organizing systems. We know what works here. We do not know what works elsewhere. This creates a difficult consequence for missions like Europa Clipper. Suppose the spacecraft detects no amino acid asymmetry, no isotope fractionation patterns, no clear organic structures resembling terrestrial biology. What conclusion follows? Scientists could responsibly say no Earth-type biosignatures were detected, but they could not honestly conclude the ocean is sterile. The absence of familiar chemistry is not identical to the absence of life itself. Some researchers, therefore, propose a different approach entirely. Instead of searching for specific molecules, they suggest searching for complexity. Random chemistry produces disorder or repetition. Biological systems produce structured information, molecular arrangements carrying improbable patterns that persist because something is organizing them. In principle, such informational complexity may represent the closest thing to a universal biosignature. But current technology cannot measure that reliably from distant flybys through frozen plumes. The instruments aboard Europa Clipper can identify molecules with extraordinary sensitivity, yet determining whether those molecules encode organized information remains beyond our present capability. So, beneath the engineering challenge sits a quieter uncertainty. Even if life exists below Europa's ice, we may still struggle to recognize it when we finally encounter the evidence. Some astronauts return from orbit unable to think about Earth the same way again. Looking down from space compresses borders into abstraction. Continents drift silently beneath thin atmosphere. Storms spiral without concern for nations or history. Psychologists eventually gave this cognitive shift a name, the overview effect. Europa creates something similar. But instead of altering your sense of geography, it alters your sense of time. The universe formed approximately 13.8 billion years ago. Within that immense chronology, Europa's subsurface ocean has likely remained liquid for around 4 billion years, sustained continuously by gravitational heating deep beneath its crust. That number becomes stranger the longer we sit with it. Complex multicellular life on Earth appeared only about 600 million years ago. Before that, for most of our planet's history, Earth belonged entirely to microscopic organisms. Vertebrates emerged roughly 525 million years ago. Land animals followed around 375 million years ago. Mammals appeared near 225 million years ago. Primates arrived much later. Anatomically modern humans have existed for roughly 300,000 years. Agriculture emerged approximately 12,000 years ago. Writing began around 5,000 years ago. Science as a formal method for investigating nature is only a few centuries old, and Europa's ocean existed through all of it, while forests spread across ancient Earth, while dinosaurs rose and disappeared, while glaciers advanced and retreated, while cities formed and collapsed. That buried ocean remained sealed beneath ice, orbiting Jupiter in complete darkness. No eyes saw it. No mind conceived of it. For almost the entire duration of human existence, Europa itself appeared merely as a moving point of light. Even after telescopes improved, nobody suspected an ocean beneath the frozen shell. The first actual evidence arrived only in 1998, when magnetometer data from the Galileo spacecraft revealed the signature of conductive saltwater hidden below the surface. That date matters profoundly. It marks the first moment in 4 billion years that Europa's ocean entered into any known relationship with conscious awareness. Before then, its tides moved unseen. Its chemistry unfolded unobserved. If life exists there, entire evolutionary histories may have occurred without ever being witnessed by another thinking species. This is not poetry. It is a literal timeline describing when information about one physical system became accessible to another. Matter organized into awareness on Earth, built instruments, crossed interplanetary space, and finally recognized a hidden ocean orbiting a distant giant planet. Only then did Europa become known. The realization changes the scale at which human history feels significant. Every empire, religion, scientific revolution, and personal memory occupies an interval so brief that it almost disappears against geological and cosmic durations. But the effect is not merely humbling. Europa also reframes consciousness itself. Most of the universe has unfolded without observers. Stars formed and died for billions of years before any nervous system existed capable of noticing them. Entire galaxies rotated through darkness long before awareness emerged anywhere we know. And yet awareness did emerge. Atoms became organisms. organisms became minds. Minds learned to measure magnetic fields around distant moons. In a universe overwhelmingly silent and unconscious, that chain of events may be among the rarest processes nature ever produced. There is another possible ending waiting beneath Europa's ice, and it is quieter than discovery. Imagine the data arriving year after year from Jupiter. Europa Clipper completes all 49 flybys exactly as planned. The radar resolves the hidden architecture of the ice shell. Brine pockets appear inside the crust. Plumes vent into space repeatedly, carrying ocean material high above the surface. The chemistry is fascinating. Organic molecules appear everywhere: carbon compounds, salts, energy gradients, water interacting with rock at the seafloor, hydrothermal systems operating for billions of years beneath stable ice. Every condition we associate with habitability is present, but the signatures never cross the threshold. The amino acids remain racemic, meaning equal mixtures of left and right-handed forms produced naturally by non-biological chemistry. Carbon isotope ratios remain geologically ordinary. Methane concentrations match what hydrothermal reactions alone can explain. No molecular asymmetry appears. No repeating biological patterns emerge from the spectra. The ocean looks alive chemically, yet sterile biologically. A later mission lands successfully. Instruments descend beneath the radiation-processed surface layer and analyze pristine ice. A cryobot eventually melts downward through kilometers of crust over many years, carrying cameras and sensors into the dark water below. The submersible reaches active hydrothermal vents at the rocky seafloor. Mineral chimneys rise through black water exactly as models predicted. Warm alkaline fluids pour into the ocean carrying hydrogen, methane, and dissolved metals. The chemistry resembles Earth's lost city hydrothermal field with astonishing precision, and still nothing moves. No cells divide. No metabolism appears. No evidence of replication emerges from the instruments. The ocean contains energy, water, organic chemistry, and immense spans of time, yet never cross the boundary between chemistry and biology. That result would matter enormously. It would not prove Europa is lifeless everywhere. Oceans are vast environments. Sampling would remain limited. Unknown ecological niches could still exist beyond explored regions. Science rarely deals in absolute certainty, but the implication would become difficult to avoid. If Europa possesses all the conditions thought necessary for life and still remains sterile, then the origin of life itself may be extraordinarily rare. The transition from molecules to self-replicating systems may not happen automatically when conditions become favorable. It may require something improbable. The great filter would shift backward toward the very beginning of biology rather than its later evolution. In that framework, Earth stops looking typical and begins looking exceptional beyond current understanding. Perhaps the universe produces habitable worlds easily, but living worlds almost never. That possibility changes the emotional scale of our own planet. Every forest, ocean current, microbial cell, and human mind would represent part of an exceedingly rare chain of events. 4 billion years of uninterrupted biological continuity on Earth would become not merely interesting, but cosmically unusual. Carl Sagan once wrote that nature is under no obligation to make sense according to human hopes. Europa may ultimately express that principle with extraordinary clarity. A sterile ocean beneath the ice would not be a scientific failure. The mission would still answer one of the oldest questions ever asked by conscious beings. The answer would simply be harsher than expected, and Earth, already fragile and temporary, would become immeasurably more precious in the silence surrounding it. At first, Europa seems to pose a scientific question. A moon beneath Jupiter, an ocean beneath ice, instruments measuring chemistry in darkness, nearly 800 million kilometers from the Sunday. The problem appears technical, almost mechanical. Build the spacecraft correctly. Fly through the plumes. Analyze the molecules. Interpret the spectra. But that is only the surface layer. Underneath the engineering sits something older and far more difficult. We are not really asking whether Europa contains microbes. We are asking what kind of universe this is, and what place conscious beings occupy inside it. That is the source of the unease. The scientists working on Europa rarely describe fear in dramatic language. Most speak carefully, methodically, with the restraint expected in planetary science. But beneath that restraint sits a recognition that the result of this search cannot remain scientifically isolated. The answer changes everything around it. If Europa contains life, even microbial life, then biology emerged independently at least twice within a single solar system, one genesis on Earth, another beneath Europa's ice, two separate experiments in chemistry becoming aware enough to metabolize, replicate, and evolve. That outcome carries mathematical weight. It means life is probably not rare. The galaxy would shift from potentially sterile to potentially crowded with living systems. Rocky worlds, subsurface oceans, icy moons, orbiting gas giants all become candidates not merely for habitability but for biology itself. But the silence would remain. No signals cross the stars. No evidence of technological civilizations appears anywhere we look. The contradiction between abundant life and cosmic silence would sharpen into something much harder to dismiss. The great filter would move ahead of us. Some barrier would exist beyond the emergence of life, beyond intelligence, perhaps even beyond civilization itself. Something would repeatedly prevent living worlds from remaining visible for long. That implication cannot be separated from the data producing it. But imagine the opposite result. Europa possesses liquid water, energy sources, organics, salts, hydrothermal chemistry, and billions of years of stability. Every known requirement for life exists there simultaneously, yet the ocean remains sterile despite all opportunity. That possibility carries its own weight. It would imply that the transition from chemistry to biology may be staggeringly improbable, even under favorable conditions. Earth would begin to look less typical and more exceptional. Perhaps consciousness is not common at all. Perhaps the galaxy is mostly silent because almost nothing living ever appears within it. Both outcomes alter human self-understanding permanently. That is why the question produces tension deeper than ordinary scientific uncertainty. A new particle discovered in an accelerator changes physics textbooks. A new exoplanet expands astronomy. But a second origin of life, or the absence of one where it should plausibly exist, changes the context in which every human story unfolds. Before and after. That is the real structure of the problem. The people designing Europa missions understand this completely. They build the instruments anyway. They calculate trajectories, shield electronics from radiation, and prepare for flybys years before the first measurements arrive. Because uncertainty this profound cannot simply remain unanswered, and somewhere beneath that frozen surface, whether silent or alive, the ocean continues existing exactly as it did before we knew it was there. Right now, while you listen to this, Europa Clipper is moving through interplanetary space. The spacecraft travels at approximately 4 kilometers per second relative to the Sunday. At that velocity, the distance between London and New York would disappear in less than 2 minutes. But space stretches scale beyond ordinary intuition. Even moving faster than a rifle bullet, the journey to Jupiter still requires 5.5 years. The machine continues outward steadily, past Earth orbit, beyond Mars, through regions where sunlight weakens into something thinner and colder. No sound accompanies the motion, no sensation exists aboard the spacecraft itself. Only guidance systems, instrument checks, radiation monitoring, and the quiet exchange of radio signals crossing hundreds of millions of kilometers. In April 2030, the journey changes phase. Europa Clipper will enter orbit around Jupiter after traveling approximately 2.9 billion kilometers through the solar system. Soon afterward, the first close Europa flyby will begin. 48 more passes will follow across 4 years, each one carefully calculated to balance scientific opportunity against the lethal radiation surrounding Jupiter. Every measurement returns slowly. The data travels at light speed, the fastest motion physically possible in the universe, yet still requires between 35 and 52 minutes to reach Earth, depending on orbital positions. A signal leaving Jupiter crosses the darkness for nearly an hour before arriving at antennas on our planet. Then scientists begin reading. Some of those scientists were young graduate students when the mission was first proposed. Some spent decades designing instruments, modeling radiation exposure, writing detection software, or defending mission funding through repeated cancellation attempts. Entire careers narrowed gradually toward a few streams of incoming numbers. Inside those numbers may sit the answer. The spacecraft also carries something less technical. Fixed to Europa Clipper is a metal plate engraved with the names of approximately 2.6 million people submitted from around the world. Beside them sits a poem by Tracy K. Smith, former United States Poet Laureate, selected through public competition. There is mathematics engraved there too. A reference to the Drake equation appears in binary notation, expressing the deeper purpose behind the mission. Nearby are reproductions of Galileo's original sketches from January 1610, when Europa first appeared beside Jupiter as a moving point of light through a handmade telescope. 420 years separate those drawings from this spacecraft. The continuity matters. Generation after generation looked upward without knowing what existed beneath Europa's surface. Philosophers guessed, writers imagined, astronomers measured faint light moving around a distant planet. Eventually, humanity learned enough physics, chemistry, and engineering to send a machine across the solar system, carrying instruments sensitive enough to taste the chemistry of another ocean. The spacecraft itself understands none of this. It possesses no awareness of what it carries or why it was built. Somewhere beyond the orbit of Mars, aluminium, silicon, titanium, and gold move silently through darkness, according to mathematical trajectories calculated on Earth. But through that machine travels something unmistakably human. Curiosity accumulated across thousands of years, and soon, for the first time since people began asking whether life exists beyond this world, the distance between question and answer will begin to close. Far beyond Mars, beyond the asteroid belt, beyond the region where sunlight still feels warm, Europa continues circling Jupiter every 3.5 days beneath a shell of fractured ice. The distance between Earth and Europa changes constantly as both worlds move around the sunday. At times they drift closer, at times farther apart. But even at their nearest, hundreds of millions of kilometers remain between the human world and the hidden ocean below that frozen crust. The ocean itself does not know this. No awareness exists beneath the ice of telescopes, spacecraft, or the species searching for answers. Whether the water contains only chemistry or something living within it, the processes there continue exactly as they always have. Currents move slowly through darkness. Minerals circulate upward from the rocky mantle. Heat rises from below through tidal friction generated by Jupiter's gravity. The system remains complete unto itself. It has existed since before complex animals appeared on Earth, before forests, before mammals, before the continents settled into their modern arrangement. While life on Earth struggled through extinctions, ice ages, asteroid impacts, and evolutionary revolutions, Europa's ocean remained sealed beneath its crust, untouched by sunlight, and unknown to every civilization that ever existed. Yet people watched Jupiter constantly. Babylonian astronomers tracked its motion across the sky around 1200 years before the Common Era, carving observations into clay tablets under desert night skies. Generations afterward gave the bright, moving light different meanings through mythology, navigation, religion, and mathematics. None knew what orbited beside it. Then came January 7th, 1610. Galileo pointed a handmade telescope toward Jupiter and noticed several tiny points of light nearby. One of them was Europa. That observation began a chain extending across 420 years of physics, astronomy, chemistry, engineering, and persistence. The chain almost broke many times. Spacecraft failed, funding vanished and returned, missions were canceled, scientists retired before launch approvals arrived. Entire careers disappeared into proposals, calculations, simulations, and arguments over whether the search justified its immense cost. But the work continued. Now a spacecraft moves outward, carrying that accumulated effort through interplanetary darkness. In April 2030, Europa Clipper will enter Jupiter orbit. Weeks later, it will descend toward Europa at an altitude lower than many commercial aircraft fly above Earth. Its instruments will open. Radar pulses will enter the ice. Spectrometers will analyze particles suspended above the surface. Magnetometers will measure the invisible electrical response of the ocean beneath. Streams of data will begin crossing the solar system toward Earth at light speed. Somewhere in Pasadena, California, inside rooms filled with monitors and quiet concentration, people will watch those measurements arrive after journeys lasting between 35 and 52 minutes through space. And then humanity will know more than it has ever known before. Perhaps the data will reveal biology. Perhaps only chemistry. Perhaps ambiguity that requires another generation of missions to resolve. But whatever emerges from those numbers will not be mythology or speculation any longer. The universe will have answered in the language of evidence. Until then, Europa waits beneath its ice exactly as it always has. Silent, dark, ancient, and unimaginably close.